So welcome back to the next session. So in this session, we would like to see first of all the pulsation in the HR diagram, and then we would like to see one case study which we recently did for one of the BE type supergiant MWC 137. Okay. So before talking about the pulsations in the HR diagram, I would like to make sure that you all have a very good understanding about the HR diagram, because when I will be talking about the pulsation across the HR diagram, probably once you know what is HR diagram, and then if you can connect some evolutionary states in the HR diagram, that will make sense to you when we study the pulsations in HR diagram. Okay. So when you look at the night sky, focus your camera on a group of stars. Okay, take the image of night sky, or you just collect a group of stars. What you will see a cartoon representation of a set of stars in this slide, actually on this page. Okay, so some of the stars, they will appear bright, some of them they will appear dim, some of them they will appear red, some of them they will appear maybe kind of blue, some of them will appear yellow. Okay, and what we do in order to put them in the HR diagram, so-called Hasbroom-Russell diagram, we try to segregate them, or we try to arrange them on the basis of their brightness first, or on the basis of their color first, and we arrange them basically on the basis of their luminosity or their intrinsic brightness and their color. Okay, so yeah, this is just a cartoon representation of the stars, a group of stars. You can see here some of them they are very bright and some of them they are dim actually. So if you segregate the stars on the basis of their luminosity, so what you will get a representation of something like that. Okay, so you have the brightest stars, brightest ones in this collection is on the top, the dimmer ones here in the bottom. Okay, and then if you basically segregate again on the basis of their surface temperature or on the basis of their color, what you will end up getting, you will getting a pattern which is something like this. Okay, so what we had initially, we had a group of stars. We just take the image of the group of stars, and now what we did, we segregated the stars, or we arranged them on the basis of their brightness, intrinsic brightness, and on the basis of their appearances in terms of color. Okay, as you know that the color can also be correlated with the temperature of the star. So it means if by convention, if I use this axis, x-axis is representing, let's say, color or the temperature, which is increasing in this direction. So these stars, they appear blue, and these ones, they appear actually red. So if I try to correlate this color with the temperature, that means these stars or stars in that region will have actually more temperature, more surface temperature, compared to the stars which are present in the right side of this plot. Okay. So now when you look at this, what you'll find that for most of the group of stars or star clusters, what you find that many stars, they are actually found or they are present in a sequence. And this sequence, what we know, we call it as a main sequence, right? What is the main property of the main sequence? The stars, what they are doing actually, what is happening in the core of the stars? Hydrogen is being converted into the helium actually. Okay. So if you look at these in these arrangements, you find that most of the stars, they are located actually in this patch of the diagram or in this patch of your graph. Okay. But we also see some of the stars, some of the dim stars, they are present here, some of them they are here, some of them they are here, some of them they are here actually. Okay. And then we ask ourselves a very simple question: why some of the stars, they are faint or they dim, and why some of them they are bright, why some of them they are actually blue in color, let's say, and why some of them they appears yellow or reddish. What is the answer for that question? Do we have a straightforward answer? Why some of them they appear bright? What can be the reason? Someone mentioned mass, obviously. If it is massive, you know the mass luminosity relation. The more massive star, typically close to the main sequence, they appear brighter, or they should have more luminosity. Okay. So it means distance. Okay. So distance can also come into the picture here. But if we focus on the intrinsic brightness, means if we talk about the brightness, luminosity of the star, in that case, obviously many factors will come into the picture. Of distance will also come into the picture. For example, unless you are talking about the intrinsic brightness or the luminosity of the star and the mass of the star itself, and maybe the evolutionary state of the star. Maybe in a particular evolutionary state, the star itself is very bright compared to the other evolutionary state of the star. So in order to answer the question, why some of them they are bright, why some of them they are red or blue, we need a kind of theoretical understanding about, first of all, formation, then their evolution, and how they end their life actually. So basically, what you need to do in order to connect the dots between these locations of the stars, some of them they appear, some of them they appear they bright, some of them they are actually dim, some of them red, some of them blue. We need a stellar structure theory, stellar structure and evolution theory in order to connect these dots actually. Okay. Yeah, so this was the question I just wanted to mention here. So obviously some of them they are bright, dim, depends upon distance, and if you eliminate the distance, if you're talking about the intrinsic luminosity or intrinsic brightness in these cases, it will depend upon how massive your star is and then in what evolutionary fate the particular star is actually. Okay. The point is that in order to understand their appearances, their brightness, we need to have a stellar structure and evolutionary theory. And Professor Glasser has already given you a brief overview about the stellar structure and evolution of the stars. Okay, so you already have some idea how the stars they evolve and what they eventually become. So I'm just going to rephrase, or I'm just going to revise the content which was actually presented earlier. Okay. Obviously, the theory of stellar structure and evolution is required in order to understand the appearances of the stars, what we see in the HR diagram. Okay. The overall evolutionary state, if I would like to just summarize without going into the details. So, stars they are formed basically from the giant molecular cloud. Okay, and when this giant molecular cloud satisfies the so-called Jeans criteria, what will happen? The star formation will trigger, and you will have a lot of stars. These stars will form, and depending upon the initial mass of the star, they will evolve and they will go through the different evolutionary phases. For example, if your initial mass of the star is less than 8 solar mass, this 8 solar mass is not exactly 8 solar mass, it depends upon the chemical composition as well, but approximately 8 solar mass. So when the initial mass of these stars are less than 8 solar mass, so eventually what they go through the evolutionary state like red giant phase, and eventually they become planetary nebula and they end their life, or they become at end white dwarf. Okay, so all the stars having mass which is less than approximately 8 solar mass, they become white dwarf. Okay, now the stars which are having initial mass greater than 8 solar mass, they go through the different evolutionary phases. For example, they become red supergiants, and they also explode as a supernova, and depending upon what is their initial mass, they either become neutron star or they become black hole. Okay, typically the value or initial mass value for the case of neutron star or to become a neutron star is in the range of 8 solar mass to 25 solar mass. So if the initial mass of the star is somewhere between 8 to 25 solar mass, the final fate or the final outcome of the star would be a neutron star, and if the mass of the star is more than 25 solar mass, the star will eventually become a black hole. Okay, so this is a typical stellar evolution kind of scenario. Obviously these values what I'm saying, 8 solar mass, 25 solar mass, they are not that strict, but it's kind of approximate value if you want to remember any value in your just for any calculation. So just to summarize, the final fate of the star is actually either the star will become a white dwarf if the mass of the star is less than initial mass of the star is less than 8 solar mass, it will become a white dwarf. If it is in the range of 8 to 25 solar mass, it will become a neutron star, and if it is more than 25 solar mass, it will become a black hole. Okay, so this is a kind of general picture what we have in stellar evolution. Now, some of the stars, you remember that when Professor Glassell was summarizing the conditions what we need for the case of hydrogen burning, so obviously we need some extreme condition in order to have nuclear burning at the center of the stars. Some of the stars, when the mass of the star is the initial mass of these, these objects, the calling them a star would be, not ideal. So when the mass of these objects or protostars would be less than 0.1 solar mass, sometimes it is also referred as 0.08 solar mass, which is required for the so-called minimum mass for hydrogen burning actually. Okay. So when the mass of these objects are less than 0.1 or 0.08 solar mass, these stars or these objects will not be in a position to burn hydrogen. So at the end, they will become kind of, they will, we call them as a brown dwarf, or we define them as a brown dwarf, and they will evolve on a very long time scale actually. Okay. So, just to summarize, we have white dwarf, neutron star, black hole, and the stars, and these objects, when the mass of your protostars is less than 0.1 or 0.08 solar mass, they eventually become so-called brown dwarf. Okay. Yeah, that is fine. So I have just to summarize you, just to give you an idea that what eventually becomes when the stars they go through the different evolutionary phases. So I would like to just name some of these evolutionary phases. You will get a PDF where these evolutionary phases will also be mentioned, so you can also take a look in detail. But the point what I would like to emphasize that what are the main evolutionary phases when the stars they go from the pre-main sequence evolution to the end of their up to the final fate, what they eventually become. Okay, so when the stars they formed from the giant molecular cloud, they go through the evolutionary phases until when the star will have sufficient conditions to ignite the hydrogen burning actually. So the evolution till the point when the star has a sufficient condition for hydrogen ignition is known as the pre-main sequence evolution. Okay, so it means protostars, I mean the stars from these protostars have been formed from the giant molecular cloud and they evolve, and obviously what they do typically they shrink, and you remember from the virial theorem what will happen when they slightly shrink, what they do, so they emit radiation and they also heat themselves, right? Are they, I mean, they also have luminosity, right? So sometimes when you say that the star is totally powered by the nuclear reaction, but these protostars, they still have luminosity even though nuclear reaction is not going on. So it means that it is clearly evident from that fact that, stars in those cases, they also have some luminosity source, right? Apart from the nuclear burning, right? So in these pre-main sequence evolutionary phases, what happens, the star slightly shrinks, and by using the gravitational potential energy or the idea of virial theorem, if you remember, they maintain their luminosity as well as they heat themselves until the point when this internal temperature or the temperature at the core is high enough to ignite the hydrogen burning. And the moment when they reach that temperature for hydrogen burning, then we call them as a zero age main sequence stars. Okay, or in short, sometimes we refer as ZAMS, ZAMS, zero age main sequence. So at the zero age main sequence, basically the entire energy or most of the energy of the star or luminosity of the star is being contributed by the hydrogen burning. Okay. And then after that, if the star is continuing burning hydrogen, we call this as a main sequence. So this is a kind of starting point of the hydrogen burning, and this is the time of the main sequence is basically the lifetime where the star is converting hydrogen into helium. After that, it goes to the another or a few more evolutionary states. For example, subgiant branch phase, red giant branch phase, and then horizontal branch phase, and then another one is asymptotic giant branch phase. In short, for example, in case of RGB, in red giant branch phase, we refer them as a RGB phase. On in horizontal branch, we call them as a HB phase stars, or in asymptotic giant branch, we call typically them as a AGB phase. Okay, and then they also go through the so-called thermally pulsing AGB phase and the so-called another evolutionary phase, which is the planetary nebula phase, and they end up being white dwarfs. So this is a typical scenario for a sun-like star or star which is of intermediate solar mass. I mean intermediate solar mass in the sense that the mass of the star is less than 8 solar mass. Okay. So intermediate mass stars, they eventually follow these kind of evolutionary tracks, and eventually they become a white dwarf. This evolutionary status would be different evolutionary processes or stages would be slightly different if you go towards the massive stars. Means if you consider the stars which is more than 8 solar mass, so obviously this evolutionary scenario would be slightly different than what we have seen in the case of intermediate mass stars. Okay. So these stars will also start the evolution after the formation as a pre-main sequence evolution. They will go through the 0 is main sequence and then main sequence, and then they will become blue supergiants or red supergiants. The case study what we are going to do probably is that star will also come into that category. We'll see later on. So main sequence, and then we have the so-called blue supergiant or red supergiant, and then they go through the different advanced evolutionary phases. Professor Glassell has already highlighted the advanced evolutionary phases where you have different nuclear bonding, actually advanced nuclear bonding. Till these nuclear reactions happen till the formation of iron core. Okay, and eventually it will if you consider the single star scenario, it will lead towards the core collapse supernova, and depending upon the initial mass of the star, it will become either a neutron star or a black hole. So this is a typical evolutionary scenario for the case of massive stars. But the evolutionary status of many massive stars is uncertain, and we do not have, or we have very limited understanding about the evolutionary states of many massive stars. Okay. So I have kind of excluded them. I have just mentioned you a kind of classical picture, a kind of nice picture where you have some understanding what the stars are actually at the end becoming. But the exact evolutionary states of massive stars is very complicated, and we have, in many cases, we have very limited understanding about the evolutionary process of these stars. Okay. Okay. So in the HR diagram, okay, let me put it here. Yes. So in the HR diagram, if I try to mark these evolutionary states, so where these evolutionary states will be, this is represented here. Again, on the x-axis we have surface temperature, or it is also referred as sometimes effective temperature. It is increasing in the negative x direction, and we have the luminosity on the y-axis. It is increasing in the positive y direction. And remember that how we represent these values. For example, particularly the luminosity, what we do, we take the luminosity of the star divided by solar luminosity and take the logarithmic, take the log of this ratio actually. Okay, this is a typical representation of luminosity in the HR diagram, and on the x-axis we take the effective temperature or surface temperature, mostly in again in log, but here I have just represented the value of our surface temperature without taking any log. Okay, so the point what I'm trying to say here is that if you need to mark these evolutionary states, what I have mentioned you earlier, so this is the location of our so-called main sequence. So this is where we have the most of the stars. If you take the star cluster and you try to find out the luminosity and surface temperature of the stars present in the star clusters, you find that most of the stars, they are actually located along the main sequence. Okay, most of the stars, if you have, let's say, several thousands or several hundreds of thousands of stars, so many of the stars or most of the stars, a substantial fraction of the stars will be present in the main sequence or on the main sequence. Do you know the reason why many of the stars, they are present on the main sequence? Why not here or any other evolutionary states? Why most of them, they are actually present on the sequence, on this main sequence? Most of the time that evolution period is more in main sequence. They stay in main sequence for most of their So one of the argument is that they spend a large amount of time on the main sequence. This is the argument, right?
Yes.
And why do they do that? What is the reason for that?
Due to hydrogen burning.
Due to hydrogen burning. And what is very special about the hydrogen burning?
Due to its content, chemical composition. Or
the chemical composition is, if you take the star, for example, in solar neighborhood, we have, let's say, 70% hydrogen, we have 28% helium or 2% metals. So temperature, any other argument? Do you understand the question, what I'm trying to ask? I said that you have, let's say, star cluster. You take the image of the star cluster and somehow you figured out what is the luminosity and surface temperature of the star cluster, and you put that star cluster in the HR diagram and construct the HR diagram for that star cluster. And what we find, that very large fraction of the members of that star cluster, means very large number of stars, they are present on the main sequence. The question is why we see very large number of stars on the main sequence. Why not in some other evolutionary state?
Abundant.
So one of the argument is that the hydrogen is present in abundant. You have 70% hydrogen. Is it that argument is correct? Any other person? Any other student? Can you think? Let me give you a hint. Can you think in terms of binding energy per nucleon? The idea of binding energy per nucleon. So remember that what we said when we were deriving in the previous class, when we were deriving the mass luminosity relations, what we said that L is proportional to m cube for normal stars, and for very massive stars L is proportional to m actually. Okay, so it means that luminosity of the star is kind of being fixed by the mass of the star, and then if you look at the binding energy per nucleon plot, what is very special about the hydrogen bonding? If you look at the binding energy plot, the conversion of hydrogen to helium is very efficient in terms of energy production. Right? So it means in order to maintain the luminosity which is being fixed by the mass of your star, you have to burn hydrogen, or you have to convert hydrogen to helium slowly, because the process itself is very efficient in terms of energy production. Okay? So it means you can burn hydrogen in a slower pace, because the conversion itself from hydrogen to helium in terms of energy is quite efficient. Okay, so what will happen at the end? It means that the star is going to maintain, or star is going to spend very large fraction of their time as a hydrogen burning. So obviously if you're taking a snapshot of any star cluster and you know that the star is most of the entire life of the star, fraction of very large fraction of the life of star they are spending on the main sequence, so obviously you will find most of them to be present on the main sequence. Okay, so that is the argument, or one of the basic argument, or one of the argument why you say that, you know, why we see many stars on the zero is on the vicinity of zero is main sequence, or on the main sequence, on the sequence actually. Okay, right? Professor Glassel, any comment on that? Okay. You have to think about it, and you know, for why star spends very large amount of time on hydrogen burning. Okay, now just to for the sake of completeness, now you see in the HR diagram what we have. This is the location of your main sequence. Okay, if you identify the location of the main sequence, and stars, how they evolve. As they evolve, they basically they go towards the so-called the this is the region when the stars they evolve, and they will reach at one point. We already discussed this point, this overall contraction point. At this, while reaching this overall contraction point, what will happen at one point? They will start running out of hydrogen at the center, and they will go through the so-called overall contraction phase, and then after that they will move towards the lower and lower effective temperature, and they climb towards the so-called RGB phase, or red giant branch phase. And after reaching the tip of the RGB phase, they eventually be in a position to ignite the next burning, which is the helium burning, and then they will go through the so-called horizontal branch phase evolution. And after going through the horizontal branch phase evolution, they will climb towards the higher luminosity, and they will go through the so-called another evolutionary stage, which is known as the asymptotic giant branch evolutionary state. So this is in short, it is known as the AGB evolutionary phase. And after that, they go through the so-called planetary nebula phase, and in the planetary nebula phase, or even in the phase of AGB as well as in the red giant branch phase, they lose very large amount of their mass actually. Okay, so the stars actually they start with a certain amount of mass, but when they end their life, you have a very, they lose at the end a very large amount of their, very large amount of mass they lose at the end when they become either white dwarf neutron star or black hole. Okay. And the mass loss processes during the course of evolution is not properly understood, and this is one of the very challenging problem in stellar astrophysics. We do not have proper idea. There are some theories and observations, but still we are struggling to explain the mass loss processes in the different evolutionary stages of particularly massive stars. Okay, so what eventually they become after going through the AGB and planetary nebula phase, the intermediate mass stars, they will become eventually a white dwarf. So they end up being white dwarf. And I have already told you that in the case of more massive stars, the stars which is more than 8 solar mass, for those kind of stars, they eventually become either a neutron star or black hole. And the evolutionary stage is more complicated and more uncertain when we talk about the massive stars. Okay, so this picture, this classical picture where you have well-defined main sequence, subgiant branch, RGB phase, horizontal branch, AGB, planetary nebula. This is kind of more simplified picture, I would say, for the intermediate mass stars or mass which is less than 8 solar mass. And when we have very massive stars, like if you have 40 solar mass, 50 solar mass, or 60 solar mass stars, it becomes quite complicated. So they do not follow the so-called regular evolutionary pattern. Okay, and that's why it is very challenging to identify or to understand their evolutionary stages. Actually, okay. This is I have already highlighted that we have main sequence, and this main sequence you have very large amount of stars. So you take the observation. Typically, the astronomers, what they do, they take the snapshot of let's say group of stars or star clusters, and they figure out what is the luminosity and the surface temperature, and they plot them like this. What we see, and then you have the so-called main sequence, and there are other stars as well. Okay, and once you know the location of the star in the HR diagram. So let me go back to the previous graph. I'll tell you here. If you know the location of the star in the HR diagram and you already have a picture about, you already have an idea about the stellar evolution. So if I give you a star and I tell you, or I specify this is the surface temperature and this is the luminosity of the star, and you also have some understanding about the chemical composition of that star, then in that case, can we comment on the evolutionary state of that star? So let me repeat the question, what I'm saying. Here we have a kind of classical picture. Stars, they are on the main sequence, they are moving, they are going through the so-called overall contraction phase, RGB phase, AGB phase, planetary nebula phase, and they are becoming white dwarf, intermediate mass stars. The question what I'm asking is that if I specify you that I have a star and the star is having particular effective temperature or surface temperature and the luminosity, can you comment about, or can you tell us about the evolutionary state of that star? If yes, how? If no, how can we do that? Yeah, so what will happen in most of the cases, you will have some idea about the location of your main sequence, right? So depending upon the chemical composition of your stars, you will have some idea about the location of your main sequence, okay? And the main sequence itself can also give you several parameters such as the age and all, so that we are not going into the details. But the point is that by knowing the location of the star in the HR diagram, for example, my star is located somewhere over here, or somewhere over here, or somewhere over here, and we have some idea, we have the idea about the mass, for example, let's say, in those cases, it will be, at least up to certain extent, you will be in a position to tell in what evolutionary state that star is actually. Obviously, it will not be very precise, but still you will be in a position to comment on in what evolutionary state you expect the star to be if the star is following the classical picture of evolution, what we know. Okay, so since we have some classical picture and kind of a classical overview about the evolution of these stars, and if you If you if you put a point here or a star here, somewhere over here, here, or here, you will have an idea that in what evolutionary state that the star should be. Okay, but you have to be careful. This is not always correct. You have to verify by some other sources or by some other analysis that in what evolutionary state a particular star is actually. Okay, but nevertheless, you have some idea that yeah, this star probably will be in that evolutionary stage. Okay. So is it clear? Any question at this point? It's fine. Okay. So now we have some kind of Professor Glasser has already given you an overview about the stellar structure and evolution, and we also have just seen that the stars they form from the giant molecular cloud. They go through the different evolutionary stages like main sequence evolution, like subgiant branch, RGB, thermally pulsating AGB, and they eventually become, for example, white dwarf. Okay. So the question now we are going to ask are if we know, if we have the understanding about this stellar evolution, and the question what we are going to ask that by having some idea about this stellar evolution, can we predict certain or can we find out certain parameters? We will come back to that point, but I would like to just diverse and come to the stellar variability part. Okay, we'll come back to this point on the evolution and finding out some certain properties of the star, but you have to just keep this information parked somewhere in your mind. We'll come back to this information and when we'll try to do the case study actually. Okay, now the topic I would like to just start is the variability of stars. The word variability itself is saying that some quantities, particular quantity or particular parameter associated with the star is going to change with respect to time. Okay. In these cases, and in most of the cases, what we mean here, or in our context, we mean that the quantity which is changing is the brightness of the star. Okay, you can call it intrinsic brightness or the luminosity of the star is changing as a function of time. So it means if you have a star, okay, and you are monitoring this star as a function of time, okay, so if the brightness of the star is changing with respect to time, so you see certain order of variability in that star. Okay, now we take our sun, let's say look at the sun in the morning from the naked eye and you try to see how the sun is changing with respect to time, how the luminosity of the sun is changing with respect to time. What we get? You will find some changes or you will not find any changes. What is going on? I mean, what will happen to the luminosity of the sun actually? Obviously, sun is rising and going up. So if you neglect that effect, typically, let's say you see the sun in the morning and try to see what will happen to the brightness of the sun. Sun is changing the brightness or not? The sun, if you look in the morning, or even if you generalize it for the case of other stars, in most of the cases, what we see, if you neglect the twinkling effect for the case of stars, the twinkling effect is basically coming from the atmosphere of our Earth, right? So you neglect the twinkling effect, okay? So if you neglect the twinkling effect, in these cases, most of the stars, what we see, most of the stars, they will be fairly their brightness or their intrinsic brightness or their luminosity will be fairly constant as a function of time from the naked eye. If you look at the stars, try to stare the stars in a very dry and clear night sky, you do not find the change in the brightness or luminosity of the star from the naked eye actually. Okay, that is also the case for the sun. If you try to monitor the sun from the naked eye, you see that in you do not find any changes. So obviously there will be some fluctuations depending upon your for example how you are detecting the intensity from a very, let's say, very crude detectors. For example, if you are trying to find out the intensity, the variations what you see is actually almost negligible. Particularly from the naked eye, you will not be able to see the differences or any changes or any variations in the luminosity of the sun. Or in a generalized sense, it is very difficult, almost impossible to detect the variations in the light which is coming from the stars actually. Okay, but what will happen when we move towards the sophisticated ground-based or space-based telescope? What is going to happen in that case? What we see now in this case, many stars, they show change in their brightness profile. So what does that mean? It means if you monitor the flux which is coming from the star, if you convert the flux into the brightness or into luminosity, and you try to plot as a function of time, let's say on the x-axis we have time, and on the y-axis we have, let's say, brightness. Okay. So when you try to see the objects from the sophisticated telescope or the ground-based or space-based telescope, so what you see, many stars, they show variations in the light profile, and some of them is they show very nice profile actually. Okay. Depending upon what kind of stars we are looking at, so you will see that they change their brightness profile, or you see the change in their luminosity on a very short, on a time scale what we can actually monitor. Okay. So the variations what we see from the ground-based and space-based telescope is observable from these telescopes. What we will not be in a position to see from the naked eye, or we cannot feel it from the naked eye. But when you move towards the sophisticated telescopes, what we see, many stars, they do not have constant brightness. Rather than their brightness is changing with respect to time, or their luminosity is changing with respect to time. Okay. So when we talk about the variability or stellar variability, here this is what we mean. It means that these stars are showing changes in their luminosity or in their brightness. Okay. Now, if you find that they change their brightness, the very first question we ask to ourselves, what can be the cause of change of the brightness of the stars or change of their luminosity as a function of time? Anyway, in the evolutionary stages, we have seen that they have been changing their luminosity like anything, right? We started from the main sequence, and while they were on the red giant branch phase, their luminosity has gone up, like in many cases, more than 100 to 1000, several thousands times from the compared to the main sequence, right? So luminosity is changing, but here the time scale what I'm talking about is of the order of few hours, few minutes, few years. Okay. So the question we ask ourselves, what is the cause of this variability? Any answer, any suggestion, any comments, or any attempt to answer this question? So you understand what I mean when I say the variability in stars, right? What can lead to such kind of changes in the brightness of the stars? Stellar dust, one suggestion. Let me start revealing the possibilities. One of the possible cause may be the star is oscillating or pulsating. Okay, and this pulsation or oscillation of the star is causing change in the brightness profile, right? So this is one of the possible origin or one of the possible explanation for the variability what we see. What about the other ones? Eclipsing binary, planetary transit, how they can change the brightness profile? Binary stars, we know binary stars, they do exist. How they will change the brightness? Exactly. So what will happen if they are in your line of sight? So obviously, if they are going to have an eclipse, So if the brightness of one star is larger or smaller than the other one, you will feel that at one point, particularly at the transit time, you see the brightness of the star will be changing actually. What about the planetary transit? What will happen in the case of planetary transit? Yes. So again, if the planet is exactly in your line of sight, and if it can block certain amount of light which is coming from the star, you will see the dip in your light. Okay. Can you think about any other possibility? In a similar context? Mm-hmm. If it accretes, it can also, yeah, can also see some. You can also see some variations in the brightness profile, because during the accretion, maybe the luminosity what you see from the accretion process can also add to the brightness of your star. Okay. Any other possibility you can think of? Obviously, there are other possibilities, but here we are mainly focused about the pulsation of the stars. Okay. So the question, for example, will be, uh, maybe for example, let's say I give you another scenarios. Maybe you have a star, and a star is having like our sun. Sun has some star spots, right? So sunspots. So sunspots is the region where you have some dark patches, and you kind of, it appears dark on the surface of our sun. This is the place where you have more magnetic field, the concentration of the magnetic field, right? And when you have large number of sunspots, so what you can also have, the sunspots can block certain amount of radiation, which is the regular radiation which is supposed to come from the sun. If you have a large number of sunspots from the sun, probably you will not be receiving the exact number of photons what you will receive without or in absence of sunspots, right? So presence of sunspots can also, or star spots can also lead to such kind of variations in the brightness profile of the stars. The question is, how can we find out what will be the plausible, or what will be the possible source of variations in the stars? Can we somehow eliminate these, for example, transit of planets, the variations which is coming from the transiting planet or eclipsing binary, or from sunspots or solar spots, or the star spots more precisely? What is the typical time scale for pulsation? Dynamical time scales, right? And if you compute dynamical time scales for the case of sun-like stars, what will be the typical value? What you will get? What you will get? Professor Glassell has already done the calculation. I have shown you that what will be what can be the possible value dynamical time scale for sun-like stars. Any rough number is fine. You don't have to be precise. 5 minutes or close to half an hour, let's say. Okay. And in case of planetary transit, what will be the time period? On the time scales of several years. Okay. So if you see the dip or see the variations on the time scale of several years, okay, and you know that this could be the possibility that the star, planet is actually performing kind of, transit on the time scale of several years, which is much longer than the dynamical time scale. So maybe this is one of the origin, one possibility. So I'm just telling you crudely how you can, kind of eliminate, or you can find out what would be the source of variability. Okay. And then if you have the idea about this rotation of the stars, you already know, for example, we can also find out what will be the rotation period of the stars. And if any changes what you see, it is compatible or it is matching with the rotation period of the stars, so then you can also link that variability with the rotation of the stars. Okay, so by comparing the time scales and knowing certain time scales in your mind, for example, rotation of the stars, what would be the typical time for any planet, any transiting of the planet. In those cases, having those time scales in your mind, you will be in a position to figure out whether what could be the origin of variabilities. Okay, but here our main focus here is that we would like to study the variability, or our intention is that the main focus or the main cause of variability in pulsation, and this is what we see in most of the cases. What you see, the variability in a very large fraction of stars, the main source or the main region of variability is actually the pulsation or oscillation of stars. Okay, so first of all, when we look at the stars, you monitor the brightness profile, and you see that the brightness is changing with respect to time. You try to see what could be the possible reason for that. And when you eliminate the other possibilities, which is coming from, let's say, eclipsing binary or planetary transit, by having some ideas about, for example, how the light curve looks, or having the idea about the different time scales, you will be in a position to figure out whether it is coming from the eclipsing binary or planetary transit or rotation of the stars and so on. Okay, but the picture what I'm or the main idea is that the pulsation in many cases is one of the primary origin, or one of the main causes to see variations in the stars actually. Okay, so pulsation, do you think that it is an intrinsic property, or it is kind of intrinsic variation, or it is extrinsic variation? What if you try to find out the in terms of intrinsic or extrinsic property in terms of variation? Obviously, it is connected directly with the stars, right? So something is going on inside the stars. So obviously, these kind of variability, what we call it as an intrinsic variability in the stars. Okay. Now, in the HR diagram, so the question what we ask ourselves is that, first of all, Professor Glasser has already pointed out that you see these pulsations and what is the possible origin of the pulsation in stars, and we have seen today different kind of modes in which the stars they pulsate. For example, some of them they pulsate P modes, G mode. Sometimes you also have the mixed mode, like the P mode plus G mode characteristics. So the one question we ask ourselves, very fundamental question, is that whether all stars they pulsate or very special class of stars pulsate. Do you know about it, or what do you think? The question is fairly simple. Let me repeat it. So I said that when you monitor some of the stars, you see the change in the brightness profile of the star is changing with respect to time, right? And if this brightness profile, change in the brightness profile is being caused by the pulsation of the star, then we ask ourselves a very simple question, whether all the stars they pulsate or a very special class of stars they pulsate. Or our instrument is not sufficient enough or sensitive enough to detect the pulsation in all stars. Maybe it is oscillating, but the amplitude of oscillations is too tiny that our instruments are not sufficient enough to detect those tiny variations. Okay, this is also one possibility. But largely, what you see that not all stars they show that kind of pronounced variability in the light profile or in the light curve. So this brightness profile, what I was telling, is many times referred as the light curve. Okay, so you have the time. So I will be using the light curve term several times. So just to make sure that you understand it. So intensity or brightness on the y-axis as a function of time, whatever curve you will get, we call it as a light curve of a star. Okay, so it looks like something. Okay, and you know the time, you know the period, right? For example, this one. Life is that simple? Obviously not. Right? Obviously not. You will not get, or in a very special cases, or in a very few class of pulsating stars, you will get that nice light curve. Otherwise, in most of the cases, you will get a complicated light curve. And then what you need to do, if you want to find out the signals from a very complicated profile, what we need to do? You have to do the Fourier transformation. From the time domain, you have to go into the frequency domain. So it means, let's make life little bit close to the reality. Okay. You'll have a signal something like that. Obviously, I'm just kind of taking any and plotting a random signal here. From visual inspection, it will become very difficult to find out what is the frequency, what is the period in the given signal in most of the cases what you see. So what you need to do, you need to take the light curve. This light curve is coming from either from the ground-based telescope or it will be coming from a space-based telescope. Okay. So what you need to do, you have to observe your star and you have this time series data, what we call it as a light curve. And when you have this light curve, what you have to do, you have to find out or you have to basically figure out what is the dominant frequencies, or maybe you will have several of the frequencies, but then you can focus about what will be the dominant frequencies or dominant period in the given signal actually, or in the given light profile. So you take the data from the space-based telescope or ground-based telescope as a light curve, and you convert this light curve into the, you perform the Fourier analysis, and you will get the dominant period out of these signals actually. Okay, and then you can ask yourself whether you will be in a position to explain or find out the origin of this period. So maybe, for example, if I'll put here frequency, so that complicated light curve will form. Maybe you have 1, 2, or maybe 3 or 4 or something like that, right? These kind of frequencies you have, or the combination of 1, 2, 3, or sometimes more than 50 combinations of the frequencies. Okay, so basically your original signal or original light curve is basically composed of several periodic signals, and then you can think about what is the dominant ones. For example, if you are interested to find out what is the origin of the dominant signal actually. Okay. So in many cases, what we do, we take or we consider the dominant signals and we try to see what is the origin of these dominant signals. Okay, so maybe you take first five or first 10 signals from your light curve and try to see what could be the origin of these signals actually. Okay. Now, before going to perform the case study, I would like to change to the another PDF where we had this different kind of pulsating stars. Okay. So what we see actually when you look at the HR diagram, the question what I asked is that whether all the stars they pulsate. Okay. And the answer is not fairly simple. Okay, it depends. But what we see, what we all agree, is that at least with the present instrumentation, it is difficult to say that all stars they pulsate. What we see, very special class of stars they pulsate. Some of them they pulsate, and depending upon in which evolutionary state they are and how close their physical properties are, we group them together actually. So in the HR diagram, depending upon where these stars, I mean a group of stars they lie, we group them these stars, and we call sometimes a collection or group of stars, a class of stars, we give them a name that this is one class of pulsating stars, and this is another class of pulsating stars, this is another class of pulsating stars. So again, can we go to the other PDF? So what does that mean? Just to, while the PPT is coming up, you see here yeah, maybe I can reduce the size. Is it visible from the back side? Okay, just let me give you the global picture and then I'll zoom it. Okay, so what you have, this is our favorite diagram. Okay, the HR diagram. On the x-axis, what you have the logarithmic temperature. Okay, surface temperature increasing in this direction as usual. You have on the y-axis, you have luminosity, which is increasing on the y direction, right? By looking at the number, don't be confused that how luminosity can be -2. You must know why it is -2. Luminosity is always positive. It is -2 because we have taken the log of the ratio L by L naught. Okay, so it's not that the luminosity itself is negative. It is just because we have taken the ratio and the log of this one. Okay, so what we have here, this is the HR diagram, and this image is taken from the book Pulsating Stars, which is written by Catalan and Smith, published in 2015. Okay, so and they have adopted it from most likely from Jeffrey 2008. What is mentioned in this plot is a different class of pulsating stars. Okay, so what you see here on the x-axis, this is the HR diagram with temperature on the x-axis, luminosity on the y-axis, and here this line, actually this location, this line is representing the main sequence, location of our main sequence. Okay, so for example here, this is the location of main sequence, and you see the dotted lines here. For example, this is one dotted line here, and this is another dotted line, and this one is the another dotted line actually. Okay, so if I plot the evolutionary track for different masses, just to make it more clear here, this is my main sequence, and if I plot the evolutionary track of the different masses, what you see here is this is what you see actually. Okay, I'm not plotting the entire evolutionary track, rather than I'm just considering a set of evolutionary track here. So on the x-axis, what we have logarithmic of effective temperature, and on the y-axis, what you have the ratio luminosity L by L naught and the log. So for example, this one may be for 4 solar mass, this one may be for 6 solar mass, the other one may be for 7 solar mass. So these are the evolutionary tracks. So it means when they start from these points, for example, these masses will start or will evolve, how they are going to move in the HR diagram. This is what is being represented by this graph actually. Okay, so the star will start, or it will start from the pre-main sequence evolution and reach to this point, and at this point it is on the main sequence, it is burning, or it is converting hydrogen into helium, and here it is moving from this location towards the so-called red giant branch phase evolution. So this is the location of RGB phase, or this is the bottom of the RGB phase. RGB phase. Okay. Okay. So this is exactly what is being marked here. What you see at these dotted lines. These dotted lines are actually marking off the evolutionary track of different masses of stars. So this one, for example, 2 solar mass, this is how it will evolve. This is for 5 solar mass, this is how it is going to evolve. This is for 10 solar mass, this is how it is going to evolve. This is 20 solar mass, and that one is for 50 solar mass. So kind of evolutionary track has been generated or has been given in this HR diagram. Okay, now you look at certain regions in the HR diagram. You see, for example, this one. I'll take any region, maybe for example this one, this region. Okay, now what has been done here, certain class of stars, depending upon the properties of their oscillation, depending upon the properties of their pulsation, they have been grouped together. So one class of star, for example, is delta Scuti. Okay, let me write it here, delta Scuti. Okay, so what does that mean? I mean, this class of stars, they are going to have certain properties which will be common, and their period would be, for example, in the range of few minutes to few hours. I don't remember the exact number, but I think if I take the number like 8 minutes or something, 8 minutes to 8 hours or 10 hours or something like that. Okay, so it means these class of stars, delta Scuti class of stars, they are going to pulsate, or they are going to show the variation in their light profile of the time scale, which is from few minutes to few hours. Okay, they are basically marked here in this region. Actually, you see here these ones. Okay, and similarly, for example, here you have solar like oscillators here, over here, and you have, for example, delta Cepheids. They are here, they are marked here. Similarly, what we have alpha Cygni variables over there. We have beta Cepheids, for example, they are over here. And then we have luminous blue variables and WR stars, Wolf-Rayet stars. LBV stands for luminous blue variables, and WR is the Wolf-Rayet stars on the top of the HR diagram. So this is the region for WR stars and luminous blue variables. Okay. For example, we have another class of variable stars, the Myra variable stars. And in addition to these, what you also have, you have some dwarf stars, particularly white dwarf stars. They also show certain variability, which is caused by basically the pulsations. Okay. So in this plot, what has been done, certain class of pulsating stars, they have been grouped together depending upon basically their pulsation properties and their evolutionary states. For example, if you look at the solar like oscillators, they are close to main sequence, or if you look at the delta Scotty stars, they are close to main sequence, or if you take rapidly oscillating AP stars, they are basically close to the main sequence. So they also have, I mean, in addition to sharing the similar kind of pulsation time scale, they also have many common characteristics, including the evolutionary states, including their surface temperature and the luminosity. Obviously, there will be slightly variation. For example, if you think in terms for the Myra variables here, what we have here, luminosity of these Myra class variables will be slightly different for those stars which are present here compared to those stars which are present here. But overall, when we talk about the evolutionary states, all these stars, all the Myra variable stars, they will be of kind of in same evolutionary states. Okay. So the overall idea here is that we have different class of pulsating stars depending upon what is their pulsation period, in what mode they are pulsating, and what is their physical properties. Okay, how close their physical properties are actually. It also helps us, for example, if you tell me that I have a pulsating star and this is delta Scotty type star, so if the moment I say it is a delta Scotty pulsating stars, you will immediately have an idea that the mass of these kind of stars will be in a certain range. For example, in these cases, the mass is like between 1.5 to 2.5 solar mass, and it will have the luminosity which is of the order of, you see here in these range actually, between 1 to 2. Look at here, close to the solar above the solar luminosity, but you have the luminosity range, you have the surface temperature range, because the surface temperature range for this class is also defined here. So by knowing that what kind of pulsating star a particular star is, it is going to help you to immediately understand that what is the origin or what is the main cause of pulsation in these stars. Okay. Now, if you look at the pulsation properties, for example, if you see here in the case of beta Cepheids or in the case of delta Cepheids, which are present over here, so these stars, obviously, what may happen that the stars, they are evolving, they are going from one phase of evolutionary state to the other phase of evolutionary state. So they will have a certain period of time when they will become variable, and after that period of time, they will not vary actually. So what does that mean? So if you look at, there is a one very special strip here. This strip in this diagram, this strip is known as the classical instability strip. Okay. What is the role of this classical instability strip, or what is very interesting about this strip? Yeah, I mean, I can explain here. So for example, let's say you have a star, and the star has started the evolution from here. It will cross this evolutionary state. Obviously, it will enter into this so-called instability strip region, and then it will pass this instability strip region, and then it will continue its evolution. While being in that region, the star is going to oscillate. The star is going to pulsate while the star is present in that region. But before that region or after that region, the star is not pulsating. Okay. So what does that mean? it is kind of telling us that a kind of special condition is required, right, in order for a star to pulsate. So when when you are going from here, for example, if you started from 2 solar mass and then the star is evolving, actually you are going from here to there. Obviously, when you enter in this classical instability strip, the star is going to show certain kind of variation. For example, if it is you're going here, so the chances are very high that the star is going to show certain pulsations. So the question is that why it is doing that, why it is not doing while it is present, or while it is just, for example, before the instability strip or after the instability strip. Obviously, one of the reason is that in order to have or in order to excite the pulsation in particular class of stars, certain conditions or certain requirements supposed to be, or certain requirement has to be met in order that star to pulsate. If those conditions are not met, the star is not going to pulsate. Okay. And what are those conditions? Master students, anybody who have used the Cepheid, particularly Cepheid variables for distance determination? Now we are coming back to the classical question: why stars they pulsate actually? What is the possible cause of pulsation in these stars? Mm-hmm. What was the kind of explanation which was proposed by Eddington? You have any idea? Why stars they oscillate? Yeah. So let me just remind you, or just briefly tell you. This is star. Let's assume that, and here we have an observer. Okay. Yeah. Forgive me for my drawing, but yeah, as long as it is giving you the right idea, that's fine. So an observer very far, we are observing a star. Okay. Think about what can be the possible cause of changes, in the brightness of the star. What can be the possible origin which can change, or processes which can change the brightness of the star? Mm-hmm. Yeah, it was proposed quite long back. It was proposed quite long back that there are two possible simple explanations for the change of the brightness profile of the star. One possibility is that the star, let's say you have defined it as star, means nuclear reaction is going on inside the star, and if somehow you are in this star in a position to change the energy generation rate which is taking place inside the star. So obviously, if you change somehow the energy generation rate inside the star, so that can lead to high number of photons or less number of photons as a function of time. So it can lead to changes, or it can lead to change the brightness of the star if any process can alter the nuclear reaction which is taking place in the star. So it can also lead to change in the brightness profile, okay, or intensity profile of the star. This is one fairly simple explanation, that the nuclear reaction itself is changing as a function of time, and consequence of change of the nuclear reactions or change of the energy generation rate is leading to change in the luminosity of the star or the brightness of the star. This is one possibility. And what was the other very famous explanation? If, let's say, energy generation rate is constant, then in that case, then if the energy generation rate is constant, maybe you have a layer inside the star. For example, this layer inside the star, okay, can act as a valve actually, okay. So it can block the radiation or it can damp the radiation for a while and then release it. Okay. So if it can block the radiation for a while and then release it, if you can block the radiation for a while and then release it, in this case, even though you are having a constant number of photons or constant flux which is coming from the core of the star, that can also lead to have, or it can lead to change in the brightness profile of the star. Okay, and this one, which is related to the nuclear reaction, is known as the epsilon mechanism. While the other one is known as the kappa mechanism. And you will hear more about these two mechanisms from Professor Glassell. Maybe in the coming lectures, you will hear more about these two mechanisms. Okay, but the idea is very simple. In case of epsilon mechanism or in case of kappa mechanism, what you have basically in one case, we are saying, or it is said that, or it is assumed that the nuclear energy generation rate is changing, and as a consequence of that change, you are having a change in the brightness profile, or in another case, even though your nuclear energy generation rate is constant, but if one of the layers inside the star is acting as a valve where the photon which is, or the flux which is coming from the interior of the star is being blocked for a while, and then these flux are being released, in these cases again you can have change in the brightness profile. So the mechanism which is associated with the nuclear energy generation rate is referred as epsilon mechanism, and while the other one is known as the kappa mechanism. Okay, if you look at the growth rate of the epsilon mechanism, so the growth rate of the epsilon mechanism is typically of the order of evolutionary time scale. Okay, so that is why it is said that the epsilon mechanism is of academic interest, and what we see in many cases, the stars, particularly in the classical pulsators, stars like delta Cepheids and all, we have the kappa mechanism, or they are basically pulsating from the kappa mechanism. Okay, and these two are the possible explanation that the star will pulsate when you see that or try to find out the intrinsic variation in the inside the stars. Okay, so I'll share you one of the few PDFs related to this class of pulsating stars, and I request you all to just go through the different pulsating class of variable stars. You will have an idea that what is the pulsation range of these stars and what is their mass and what is the other physical property of the stars. So you will have some idea about these different groups of stars actually. Okay. Now, if you can go switch to the case study actually, or if you have any question at this point. Okay. Now, again, can you distribute? We had one nature diagram already given. Okay, perfect. So we have a very special kind of star. Okay, the name of the star is NWC 137. Okay. Now the astronomers, they have given us the surface temperature of the star. They have determined the surface temperature of the star, and the surface temperature of the star is 28,200 Kelvin. Okay, so we know the surface temperature of the star, which is of the order of 28,200 Kelvin. Luminosity, on the same, the way we know or we have been using so far, luminosity of the star is given as 5.84. It's a number, right? Because it has been normalized and we have taken the log. From the TACE is actually transiting exoplanet survey satellite. It is a space-based telescope which is actually mainly for detecting exoplanets. So in order to detect exoplanet, what you do, if your instrument is relying on the transit method, so in that case you basically monitor a star very long period of time. Okay, and while monitoring the star very long period of time, for the transiting of the exoplanet, what you also get, you'll get the kind of brightness profile of your star. So it's a kind of byproduct of these exoplanet missions, so that we have very large amount of data where we see the brightness profile of the stars. Okay. Now, when this star is observed by the TESS, the dominant period was found to be 1.9 day. the light curve in the sector 6, for example, on the x-axis, but we have the brightness, which is basically given in terms of magnitude here. So magnitude, brightness in the magnitude is given, or change in the magnitude is given on the y-axis, and on the x-axis you have kind of time actually. Okay. So the first question we ask that how this number is coming into the picture, 1.9 day. Obviously, what you need to do, you need to convert this light curve into in the frequency domain, and you see what is the dominant frequency. Obviously, there are many frequencies, but at the moment, let's say we are interested in the dominant frequency. Okay. So if you do that, if you take this light curve and convert it into the frequency, you will find out that the frequency, the dominant frequency, or the dominant period associated with the frequency will be of 1.9 day. Okay, and we ask ourselves, can we explain somehow, or can we find out that what is the origin of this 1.9 day variability in this MWC 137? Okay, so how can we do that? Obviously, in order to do that, what we need to do, or in order to compare these frequency from from models, what we need to do, we need to construct the models, perform the linear stability analysis, what Professor Glassell was telling you in the morning and yesterday. We need to perform the linear stability analysis, and the result of the linear stability analysis is kind of, eigenfrequencies. You will have a set of eigenfrequencies, and in these set of eigenfrequencies, you try to see which one is excited, which one is damped, and by comparing the excited frequency with the observed ones, you see whether we will be in a position to explain this 1.9 day variability. Okay, so in order to construct the models of the star, what you need to know first of all the surface temperature, luminosity, and there is another parameter. That parameter is the most important parameter for star, mass. Okay, so in order to construct the models, what you need obviously effective temperature, luminosity, chemical composition. Let's say we already know that star is having the solar chemical composition. So in addition to these information, what you also need, you need to have mass. The question is, by knowing these two, can we find out the mass? You have probably a paper is given to you. If you look at your paper, so you have some evolutionary tracks on the paper. Okay. So in this sheet of paper, the evolutionary tracks of 4 different masses are mentioned here: 30 solar mass, 45 solar mass, 70 solar mass, and 100 solar mass. Okay. So if I tell you what is the surface temperature and what is the luminosity, because these are the two quantities what you can easily measure, right, from the telescope, or having some idea about the distances, we can measure these two quantities, surface temperature and luminosity. Mass is little bit difficult unless you have a binary system. It is quite difficult to find out what is the mass of the star is. Okay, so the question is that if we have some understanding about the stellar structure and evolution, and we know that how the evolutionary tracks they look like, can we find out the mass of the stars, approximate mass of the star, not the exact obviously, approximate mass of the stars, if I only tell you the effective temperature and the luminosity of the star? So just maybe we'll take a couple of examples and I see whether you are in a position to do that. So let's say we have a star, I name it as a object A. Okay, and for this object A, we have the luminosity (5.4) and the surface temperature equal to 4.4. I think if you convert it to normal Kelvin scale, it is close to 25,000 Kelvin. Can you tell me, by looking at this evolutionary track, what will be the approximate mass for this star? 30 solar mass. Very good. We'll take another one. 5.9, let's say luminosity is 5.9 and effective temperature is again 4.4. 5.9 and then 4.4. Logarithmic scale, this is luminosity and this is temperature. Now what will be the mass? Approximate mass, obviously. Can you find it out? Or you need more evolutionary tracks, or you can at least give me a range. Give me a range around 70. Do you all agree with that? There is another number is coming 50 to 55. Anyone else? 60 to 65. 62. Similarly, when you read the papers about the deriving the mass of these different stars, you also get the range of mass. You will not get the exact mass. You will get, like, in some of the papers or in some of the literatures, it will be claimed like 30 solar mass, 35, 40, 45, 60, and so on. Okay. So the point what I'm trying to say is that you can have an estimate about the mass of a star if you know the evolutionary tracks. Okay, obviously in order to generate the evolutionary track, you need to assume what is the chemical composition, and by assuming the chemical composition, you can actually generate the evolutionary track of these different stars. And if you have the evolutionary track, then what you can do, do we have evolutionary track here in this PDF? It's fine, it's not required. I can draw here and then. So for example, the typical strategy is, let's say you have effective temperature. You have already done that. Just for the sake of completeness, this is for example 30 solar mass, this is 40 solar mass, this is maybe 49 or 48 solar mass, and this is, let's say, 57 solar mass. Okay, this is the evolutionary track associated with the stellar model having that initial mass. Okay. Now if I'll tell you that what this particular luminosity and the effective temperature, you say for example you have a effective temperature and luminosity, and this is somewhere over here. Okay, then you say the mass of the star would be close to maybe for example 49 solar mass. Okay, because the evolutionary track of 49 solar mass, maybe it will pass through this position actually. Okay, so the point is that by having the evolutionary tracks, or by knowing the evolutionary tracks of particular chemical composition and knowing the effective temperature and the luminosity, you can find out or you can estimate the approximate mass, a kind of crude mass of the given star. Okay, and what will happen when you have large uncertainty in your luminosity itself? Then the uncertainty in mass will also be there. Then you will not be in a position to specify what is the exact mass of the given star. Most of the cases, this is what we face actually. Okay, so what we have large uncertainty in the luminosity of the star because we do not know exact distances, or there are some other physical constraint where we cannot specifically fix what is the luminosity of the given star. Okay, so in this case there is also error in the luminosity determination, but the point is that we have some understanding. You know that what will be the approximate range of this, what will be the approximate or plausible mass for the star, if you know the effective temperature and the luminosity of that star. Okay, so instead of relying on a single model, the best strategy would be that you create a sequence of models and you analyze or you perform the same study for a sequence of model rather than doing for single model actually. Okay, so whenever you have to perform or you would like to construct the so-called hydrostatic model, or you would like to perform the linear stability analysis, the strategy would be that you consider a series of models, a sequence of models, which will take into account the different masses or different luminosity or different effective temperature. If you find that the particular parameter is uncertain, and in most of the cases what we see that it is the mass where we lack, we lack the information about the mass of a particular object, particularly the stars which are field stars and they are not in a binary system. Okay. Oh. Yes, so I said that the dominant period is 1.9 day. But why should you believe me actually? You should have asked me the proof. And the proof is here. Okay. So if you convert into the Fourier domain, or if you plot the periodogram for the signal, what you will get a dominant peak, and this dominant peak is close to 1.9 day. Okay. And this graph is actually, I should first put the credit here and then continue the discussion here. So this graph is actually coming from the paper which is published by Sogyan Parida et al. 2024, and he is over there. Okay, the credit goes to him as well as the publishers. Okay, so you see that from the light curve what we have, you have the periodogram where you know what is the dominant period in your signal, and this period is 1.9 day, and this is why I have written here 1.9 day. And this, in fact, the same analysis was also done by other research group, and they also claimed, or they also found that this is 1.9 day. They did it first and we did it again, and both of us, or both the groups, agree that the dominant period is 1.9 day in this star. Okay, now the question is how to find out and how we can explain this dominant period of 1.9 day. First of all, as I told you, we need to find out the mass of the star, a sequence of mass. I mean, what is the range of mass for this star? Okay. The luminosity which corresponds to the luminosity which was mentioned is over here, and the surface temperature is over here. But if you look at the error in the luminosity, this is the error. Okay. So this is the error in the luminosity, or luminosity by some other authors has also claimed that the luminosity of the given star is actually in this range actually. So we have taken a kind of possible range of luminosity for this star, and we have also associated with the possible range of the effective temperature or the surface temperature of the star in this graph actually. So what is plotted here on the x-axis, again our favorite quantity, surface temperature of the star on the x-axis, and y-axis we have the luminosity. The different lines what you see here, for example the red ones, blue ones and all, they are representing nothing but the evolutionary tracks of a different mass of the particular model. So for example this one is representing 54 solar mass, this one is for 50 solar mass, this one is 44 solar mass, and this one is, the red one is 46 solar mass. Okay, so the different lines, they are indicating the evolutionary track of the same chemical composition but different mass actually. So these evolution tracks, they are representing the different evolution tracks of different masses actually. Now if you see and try to see which mass is actually coinciding with this one, so you see a mass which is close to 48.2 solar mass is actually passing through the location, kind of an average location of this star. So we have some idea that maybe the mass of the star is close to 48 solar mass, but we still don't know because there is a large uncertainty. Or the previous authors, or previously it has been reported that the star also has a luminosity which is ranging from 5.95 or close to 6 to 5.7 actually. Okay, so in this case the mass, there is a huge uncertainty in the mass determination when we try to use the evolutionary track. So best strategy would be that we consider a sequence of mass. So what we did, we considered 27 to 70 solar mass. We said that okay, let's take a range of mass where we will perform our analysis. So what we did, we have taken a range of mass 27 to 70 solar mass, and the motivation why we did that actually, because we are not sure what will be the exact mass of the star, and later on we'll be we'll be in a position to constrain, the mass, what should be the mass of the star if the variability is caused or if variability is coming from the pulsation of stars. Okay, so that you should keep in your mind. We'll come back to this point later on. Now, this diagram, what we have here, so what you do now, you have a range of mass and you already have parameters. Mass, you have already mentioned here, 27 solar mass to 70, right? 70 solar mass. And you have effective temperature. It was 28 Kelvin and the luminosity was 5.8. Right? You can verify by going back. 5.8 more precisely. Yeah. Yes. Yeah, so depending upon how you are measuring your distances actually, so obviously luminosity will also depend upon the distance, and if you have some error which is already present in your distance determination, so that error will also propagate in the luminosity determination. Okay, so it depends upon the way we are measuring the distance of that star, so the same error will also propagate in the luminosity determination. Okay, so now if you have these parameters, mass, effective temperature, luminosity, what we can do, we can construct a sequence of model considering the solar chemical composition. For the case of solar chemical composition, what typically we use, as I have told you in the previous one of the previous sessions, if I take right in terms of percentage, this will be 70%, y is equal to 28%, and z is equal to 2%. If you write z in terms of fraction, or if you write x in terms of fraction, that will become 0.7. If you write z, that is representing the metal content for the solar chemical composition, that is 0.02 in terms of fraction. Okay, because if you add them together in percentage, it has to be 100. In fraction, it has to be 1. Okay, so that's how it is mentioned here. So for construction of the sequence of models, we have taken this parameter, and what you see here, what we have done here, we have plotted the so-called modal diagram, where on the x-axis you will have one of the stellar parameter. In this case, we have taken mass, and on the y-axis we have the eigenfrequencies. And when we perform the non-adiabatic radial frequency analysis, the frequencies will be, the eigenfrequencies will be only real. The eigenfrequencies will be complex. So it means you will have the imaginary part as well as the real part. So your sigma will be sigma r plus I sigma I. Okay. So what we have done, so I will just briefly explain you what is the modal diagram, so that it will make sense to you. Otherwise, it will be difficult for you to digest what I'm trying to say here. So what you can do, actually, you can calculate the set of eigenfrequencies for a given model. So if you construct one model, let's say for 27 solar mass, you have your sigma r, and obviously sigma r plus sigma I will be there. So if you take one of the models, for example, let's say I have taken 27 solar mass model, what you'll have an infinite set of eigenfrequency for the single model. So what does that mean? We have constructed the hydrostatic model for 27 solar mass model, and then after that we have performed the linear stability analysis for this model. And when we perform the linear stability analysis for this model, what you will get? You will get the infinite set of eigenfrequencies. Okay, so it will have the imaginary part plus real part, imaginary part plus real part. So you can bifurcate this imaginary part and real part and plot them independently. For example, so if I'll take only the real part here, real part of the eigenfrequency. So what you will get for one model, you get, for example, large number of these infinite set of eigenfrequencies, right? Similarly, if you compute it for the next one, you will again get the infinite set of eigenfrequencies, and if you do it for all these models, whatever you have considered, for example, in these cases, what you will get kind of you will get a kind of line like what I have shown here. Okay, if they are very close to each other, obviously. In these cases, we have taken large number of very dense grid actually. So if you have the dense grid, obviously these dots what you see, they will look like a line actually, but in reality they are so dense that you see a kind of a simple line actually. Okay, so this is, for example, the first one, second, third, fourth, fifth, and so on. And similarly, what you can also have, you can have sigma I, and obviously corresponding to sigma R, you will have sigma I. So this sigma would be sigma R plus I sigma I. So corresponding to sigma R, you will also have sigma I, and then similarly you can also plot the same thing. And this is what it is done here. Okay. So what we have taken a sequence of model 27 to 70 solar mass and calculated the eigenfrequencies for all these models up to certain values. Obviously sigma R, for example, in these cases close to 5, or yeah, plotted here we did it for more than 5, but plotted here up to 5. Okay, sigma R is 5. Okay, why it is 5? Why there is no unit for this one? Do you remember the discussion Professor Glassell mentioned? What we did? Yes, we made it unitless by normalizing it by global free fall time scale. Okay, so these quantities are normalized by the global free fall time scale, and if you have to convert it into the time or into frequency cycle per day, then you have to get or take or adopt the same parameters what you use for normalization, and you have to multiply that parameter again to get it in a original form actually. Okay, so what you see here, interestingly, what you have blue line, and this blue line, they are indicating these eigenfrequencies where you have sigma I below 0. So for these blue lines, we have this special situation. Okay, if I'll delete this one, for sigma, for these kind of sigma r's, what we have sigma I less than 0, and for rest of them sigma I is greater than 0. And we are saying that the frequencies where sigma I is less than 0, they are excited, or they are associated with the unstable modes. Why? What is the reason? Can you think when we did the separation of variables while writing the linearized pulsation equations? So when we perform the separation of variables, what we did? How we wrote the time dependence? E to the power or I sigma t. Let's say we have one spatial, for example, if I write, let's say q depends upon maybe x and t, and if you write it in terms of another variable, it depends upon the background model or background or independent of time. And then another one is, for example, e to the power I sigma t. So in this case, if your sigma is equal to sigma r plus I sigma I, what will happen if sigma I would be negative, or what will happen if the sigma I will be positive? Can you just do the calculation? Is it possible for you? You see what we said, that we have taken this linearized pulsation equation, and this linearized pulsation equation, in the case of radial perturbation, it is forming a fourth order eigenvalue problem. And this fourth order eigenvalue problem, when you solve it, you will get the complex eigenfrequencies. Okay, and in this complex eigenfrequency, obviously you have real part as well as the imaginary part. And by considering how we have taken the time dependence, I'm saying that here in this frequency analysis or in this diagram, sigma I is less than 0, then I'm saying that the modes are excited, or the frequencies associated with the particular mode, the modes are actually excited or unstable. Can we show that from that dependence from here? Is it possible? Did you try by yourself writing down the linearized form of radial pulsation equations? Yeah, anyone else? You are running out of time. Yes. Simply take. Probably you don't have to take derivative. You simply just take, it depends upon how you are taking the time dependence. For example, some in some notations you can also have e to the power minus I omega t, and sometimes you can also have e to the power plus I omega t. And you look at the situation where your sigma I is negative and sigma I is positive, and if you look at the situation, what will happen in one case, the solution will favor towards the exponentially growing situation, and in other case it will be the opposite, so exponentially decaying situation. And you can just test it by putting sigma I negative or positive, depending upon how you have taken how you have taken the time dependence. Okay, I suggest all of you, strongly suggest you do it by yourself. Okay, so what it will lead, it will lead to the fact that whenever you have sigma I which is less than 0, your modes actually will be excited, and whenever your sigma I is greater than 0, in those cases your modes would be damped actually. So the modes which is represented by here, the blue lines actually, thick blue lines actually, they are having a negative imaginary part. Okay, negative imaginary part means they have basically sigma I below 0. So for example, you see here we have one mode for which the value of your sigma I is less than 0. Obviously it is 0.4 for the case of one model which is close to 27 solar mass, and it is going towards 0, but it is still negative, and it will still negative even up to here. So this is basically, this correspond to this mode which is being represented, or which is over here. Okay, and some of the modes where you see this sigma I is negative, these ones for example here, and they correspond to the modes what you see here actually. So whenever you have sigma I less than 0, these modes are actually indicating that these modes are unstable, or these modes are actually excited, and we are very much interested in those modes. Okay, what will happen when we perform the adiabatic linear analysis, adiabatic linear radial analysis? Do we get that information from there? Can we comment upon, or can we comment on the fact that the mode is excited or not. Because in that case, what you'll have sigma that will be real. So in this case, it is almost difficult to comment on whether the mode is excited or damped because you don't have sigma I there, right? So that is why it is always it is advisable whenever you're trying to study or trying to compare something with observation. It is always advisable to go for non-adiabatic analysis and you try to solve the eigenfrequencies where you also have the real plus imaginary part, so that you can have the information about, or you have the information about the excitation or damping of a particular mode. Okay, so what we see here, that few modes, at least 1 2 3 4 5 6 7 8 and 9 modes, out of consider these modes, they are actually excited. Okay, now if we try to plot it in the period, and we see, if we try to plot it in the period and then we try to see whether we see this 1.9 day variability what we have observed using the test. Yeah, so I will skip it. It is just the same model diagram. So this is known as the model diagram where you plot the eigenfrequencies, the real part of eigenfrequency and the imaginary part of eigenfrequency as a function of one of the scalar parameters. In this case, we have used the mass. Okay. So this quantity, when we plot the real, imaginary and real part of eigenfrequency as a function of scalar parameter, we call that diagram as a model diagram, and this is very famous when we try to theoretically see whether particular mode is excited or damped. Okay. Now, when you take that same model diagram for solar chemical composition and you try to see on the, instead of plotting in the normalized frequency, what you plot, if you plot as a function of mass, but instead of taking the frequency sigma, what you take the period, right? Period of all the modes, period of associated modes, right? One particular mode will have a certain period for a particular given model. So now here, what you see on the x-axis, again we have the mass. On the y-axis, we have the period associated with these modes. And 1.9 day period is basically marked by this dotted line here. This is what you see. And this 1.9 day is the period what we have already observed using the test. So this is the location of a period which we have observed actually. Now, if you look at this observed period, so what you see, one of the modes here, for example, this one is actually crossing at this point where this mode is exactly having a period of 1.9 days. Okay, so it means that this period 1.9 day can be explained by the radial pulsation if the model of your star is close to 45 solar mass. Okay, what about the other possibility? So we have another mode which is excited and it also has a period of 1.9 days. And the mass of this model is close to 33 solar mass. Okay, so what we have found, we have performed the linear stability analysis and we found there are several excited modes, and we also know the period of these excited modes. And out of all these two modes, we found that these two modes, they have exactly identical period what we have found in the test data for the star MWC 137. Okay, can we eliminate this one or any one of them, because now the two models, they are explaining that period. Which one would be more favorable and what will be your argument? So now let me just rephrase the question. We have two modes and these modes are excited. I mean, there are many modes, but out of these many modes, two modes, they have for a certain mass, for example, this mode for 45 solar mass, and this mode, for example, 33 solar mass, is exactly having 1.9 day period. Okay, so which model is going to explain the 1.9 day variability in our star? Obviously, you can think about Again, you go back to the HR diagram and you see whether 33 solar mass will be a reasonable value or reasonable mass for a star which has 5.8 solar. So look back your graph again and you see that whether a 33 solar mass is going to have a luminosity which is of the order of 5.8 solar luminosity. Probably not, but obviously we don't know actually. That information we don't know, because if the star has lost a very large amount of mass, again we don't know. Maybe the star can have that amount of mass, but typically in a usual star it is difficult to have 5.8 solar mass luminosity. But again, since there was uncertainty in the luminosity, it will be difficult to comment on that, whether how to exclude this one actually. Okay, but what you can also do, Professor Glassell, he will be telling you about the non-linear numerical simulations. So you can also take the help of non-linear numerical simulations, and you can also see what would be the actual mode which is going to explain 1.9 day variability. But for the sake, we are assuming that we don't know still how to perform the non-linear numerical simulation. So pretending that we don't know that, so what we say that, or one of the argument may be that it appears that, we say it appears, you cannot claim that, right? So that it appears that this model, which is having the mass of 45 solar mass or close to 45 solar mass, is going to explain the observed period, which is of the order of 1.9 day. Okay, so what you see here, because this 1.9 day is exactly matching with what we have observed in the case by using the test data. So at least now we have kind of some assurity, up to certain extent we are sure that this model 45 solar mass model can explain the variability, which is the dominant one, 1.9 day variability in our models of MWC 137. And if we believe that the variability of this star is being caused by the pulsation, let's say more precisely radial pulsation, then the mass of the star is likely to be either 45 solar mass or 33 solar mass. And once we have some idea about the non-linear numerical simulation, maybe we'll be in a position to comment on which one is going to be more plausible mass. But what we see that the 45 solar mass are supposed to be the typical mass for this star MWC 137. So we can, in this way, we can also constrain if you have the information about the oscillation of the star, and this way you can also constrain up to a certain extent what would be the fundamental parameters such as mass for the given star. Okay, any question at this point? Maybe I invite Professor Glassell for any comments. No? Okay. So just to give you an overview what we did actually. Okay. So that you know what we were doing actually. So we observed MWC 137 just by luck or maybe by someone's plan, and it was found that the period of this star is 1.9 days. Okay. The test mission is one of the, what I would say, currently it is observing very large number of stars, and on a very fruitful mission for people who are studying the stellar pulsation or seismology. It is very useful. It is observing very large number of stars actually, and MWC 137 was observed in several sectors, and in 2 or 3 sectors we find that the star is actually consistently showing 1.9 day period, dominant 1.9 day period. So obviously 1.9 day period in this star is not just just by chance or some numerical artifacts. We are quite sure that this is the period where the star is actually showing 1.9 day is a dominant period in this star. And then the question arises that what is the origin or what is the cause of this variability, 1.9 day variability, right? And then we constructed the models, by assuming that the sequence of models and so on, and we performed the so-called linear stability analysis, and there we found the set of eigenfrequencies, okay, where we had real and imaginary parts, and from the imaginary parts we came to know the excited and damped modes, and by analyzing the damped mode we came to know that one of the the two models were explaining this 1.9 day, and looking at the luminosity of the star, what we say that the model with 45 solar mass is closely, or at least it is explaining what we observe. And if you look at the 45 solar mass, it appears to be more reasonable compared to 33 solar mass. Obviously, for 5.8 luminosity on the logarithmic scale, 5.8 luminosity is quite high for 33 solar mass star. Okay, so it means that the 45 solar mass star is in our models of 45 solar mass star is in a position to explain what we observe, this dominant variability of 1.9. Okay, or vice versa, we can also say that with the help of 1.9 day variability, you can also constrain the mass of the star, which is close to 45 solar mass. Okay, so we'll come to this problem once again once Professor Glass will discuss the nonlinear numerical simulation. So maybe if the time will permit, we'll briefly discuss the outcome of the nonlinear numerical simulation here. So I have omitted because that part has not been discussed in the class. Okay. Okay. Any question? Yes. Yes, you can you give mic?
Is neglecting the 33 solar mass possibility maybe due to the fact that we have the stable and unstable condition at the same point at that 1.9 period for that mass?
No.
Because
You see here you have, for example, you mean stable or unstable? This one.
yes, sir.
Probably that is not the reason. The reason why we say it is you can neglect is because the mass of this star 33 solar mass appears to be very low for 5.8 logarithmic scale L by L's and 5.8. Okay, so that's the argument we generally try to give. Not that this is because we have stable and unstable at the same point. Okay. And another possibility would be that you can look at the imaginary part as well. And what you can see for one model, you can have more than one excited modes actually. Okay, and so, but even if you have at least one, or if you have more than one, depending upon the strength of your instability and what the final consequences will either be regular or semi-regular pulsations, that we will only know once we perform the nonlinear numerical simulations actually. And here, in the case of linear stability analysis, we only have the information mode is excited, mode is damped, and if excited, what is period of excitation. Okay, that's the only information what we get actually. Remember that even if you try to find out the eigenfunctions, Professor Glassell has already pointed out that it will not be possible to find out the final amplitude. Okay, so in order to find out the final amplitude, we have to rely on the non-linear numerical simulations. So linear theory is only going to tell us how many modes are there, and out of several modes, which one is excited and which one is damped. And by comparing these excited modes with observation, you will have an idea that is there any mode which can actually closely explain the observed frequency. Okay, but again, this is linear theory, so we have to also consider the non-linear simulations before making any conclusion. Okay, but at least it gives you an approximate way that this is one possibility, that we see that star is pulsating in the same period, and we also have the similar excited frequency in our models. Okay. Yes, there's another question.
Sir, in kappa mechanism, how photons are blocked by interior surface?
Yeah, that's an interesting question. Okay. So typically what you see, the kappa mechanism and epsilon mechanism probably will be discussed tomorrow by Professor Glassell, but just to give you an idea, basically what happens in the case of kappa mechanism is that during the phase of compression, what you need in order to have a cycle, what you need during the phase of compression, you need to have higher opacity. Okay, during the compression phase, you need to have a higher opacity. Okay, so if you remember the opacity plot, we had 3 peaks actually. This is the surface, and this is the center, towards the center of the star. Temperature is on this axis actually. So surface temperature somewhere would be here, and the core would be somewhere over here. Okay. So what we see, I don't remember exactly which peak is higher than the other one, but I'm talking about the 3 peaks. So just if you can focus on these 3 peaks. You remember what is the origin of these 3 peaks? And these 3 peaks belongs to yes. The first one is hydrogen and first helium. What about the second one? Helium 2. What about the third one? Heavier elements, right? Iron group element or iron opacity. Sometimes it is referred as iron opacity bump. Now, typically, if you try to see that what can be the cause of when you want to have a situation where during the compression phase you need to have a higher opacity. So opacity is like the measure of how you allow the photon to escape from the medium. Actually, higher opacity means you will not allow the photons to easily escape from the medium. So more opaque your medium is, the easily you will be in a position to trap the photons actually. Okay. So during the phase of compression, what you want to have higher and higher opacity. So during the phase of compression, if you have higher opacity, what will happen? Higher opacity will basically damp the radiation. So higher opacity will basically block the radiation to go out. And when it will block the radiation to go out, what is going to happen? It is going to exert, kind of pressure, and the star is going to expand a bit. Okay, but during the compression phase, how it can be achieved? If you see these 3 regions, particularly these 3 regions, the opacity in these 3 regions. So these regions, for example, here to here, we plot it here. If I'll put it here, this is the region. If I plot it here, for example, this is the region, and if you plot it here, this is the region where, as a function of temperature, your opacity will actually increase. In rest of the cases, in rest of the material, typically what you find in a large fraction of, in the large portion of stars, what you find, as the temperature is going to rise, your opacity is going to decrease. Okay, so as your temperature is increasing, your opacity is going to decrease. While what we need during the compression phase, obviously what is going to happen? Typically the temperature is going to increase. So in those cases, when you try to whenever you have the compression situation, and one of these zones, actually one of these regions where your opacity is high, when you are, even though the temperature is increasing, if one of these regions are located at a proper place, they can act, if you remember the valve what I was mentioning, these regions can act as a valve, and what will happen during one of the compression phase, you have higher and higher opacity, it will damp up the radiation, and then it is going to release after a while, and then this cycle will actually will be repeated again and again and again. Okay, so this is what eventually it will lead to a kind of cycle, or kind of a repetitive pattern. Okay. Okay, any other question? Yes, that will be discussed by Professor Glassell. So maybe the experts will take the answer and answer it when the time will come. Okay. So we'll talk in detail about the strange mode instabilities, and you will hear other possibilities. So the kappa mechanism, just to comment on your question, the kappa mechanism is actually a kind of mechanism which depends upon the thermodynamics of your system. Okay. So these mechanisms, if you switch off the specific heat capacity, if you switch off, somehow, if the thermodynamics will not play a key role in those kind of circumstances, then these kind of mechanism cannot operate. But you will see the strange mode mechanism or strange mode instabilities, they can act even though you disregard the specific heat capacity of the medium actually. Okay, so the strange modes, they are of mechanical origin, and that will be demonstrated in the coming lectures. Okay. Okay, so if not, we can close our session here. Okay. Any question? So why one of the excited mode is also present in the other one, other excited modes? For example, this one is also present in this one. These ones you mean? So the let me just go to that one. This one, right? The 33 solar mass is having two excited modes, you mean, right? So you see, the number of excited mode will depend upon the model itself. So for example, one model you may have where you do not have any mode which is excited. It actually refers us to a very larger question, or very nice question, that you have infinite set of possibilities in a stars, means you have fundamental mode, first overtone, second overtone, and so on, right? And out of these infinite set of possibilities, which mode will be excited, how we are going to define, how the star is deciding which mode is going to be excited. Fundamental, first overtone, second overtone, third overtone, how particular mode is going to be excited. Because we said, if you remember, that in the classical picture, when we have this Sturm-Liouville problem, in those cases, what you have seen, that you have kind of infinite set of discrete eigenfrequencies, right? So you have multiple frequencies, infinite set of eigenfrequencies. So you have infinite set of modes actually, and out of these very large number of modes, which mode will be excited and which mode will be damped, how we are going to decide actually. Okay, so we have certain idea about the possibilities. So for example, I'll just give you an idea that in some cases, what you need to have, this valve which I was talking about, that has to be located, or that has to be present in a special in a special zone, where you can have the conditions which are required for the excitation of your pulsation. Okay, so basically, which mode will be excited and which mode will be damped will depend upon the, first of all, structure of the star itself, and then the location or the zones which are favorable for exciting the modes. For example, these regions, where these regions are present. If your node of a particular mode is exactly lying in the middle of this one, for example, if you have a node over here, okay, so what do I mean when I say node? If you remember that, this is star, and we are considering it in a one-dimensional aspect, right? So in terms of like organ pipe, what you will have, you can imagine the situation. What you will have kind of one mode which is excited, and the other one is, for example, fundamental mode. In the case of fundamental mode, what will have, or the first possibility, where you have this kind of mode, right? So if you take this string, one-dimensional string, that will be more ideal to understand it. So if you have a string, one-dimensional string, if I close this string both ends, the fundamental mode will look like something like this, and the first overtone, for example, will be something like this. Okay, it will have one node between these two boundaries, actually these two closed boundary. If you have second one, you will have two nodes. If you have fourth one, you will have, that's how the number of nodes they are going to increase. Now in case of stars, this is also, if you take the analogy of this one and try to see in terms of stars, obviously star would be like one end, it will be open organ pipe, other one is the closed one. So in that case, again you ask yourself whether in these favorable locations, whether your modes have node or antinode. If the node is present, obviously, then it's not a favorable condition actually. Okay, so first of all, these zones which are favorable for the for the excitation, and the mode associated where you have these nodes and antinode, these combination of these effects is going to determine the star is going to oscillate or not. If yes, what would be the possible modes of oscillations and so on. Okay. Uh-huh. Not always. Yes, that's a good question, Akhil. So the question is, can we rely all the time in the HR diagram to exclude that mass? Probably not, because in some of the stars, what we see, they generally go through very extraordinary amount of mass loss during the evolutionary process. So you cannot just thoroughly exclude the possibility. But what you rather say that the favorable condition would be for this model actually, and then you can also rely on the non-linear numerical simulations, and you try to see whether these numerical simulations are also giving the same results or they are actually deviating from the linear one. But yeah, sometimes it helps just to imagine the situation that you have a 33 solar mass and the luminosity is like 5.8 in terms of logarithmic scale. That number is too much for 33 solar mass. Okay, so that's how we typically we say that possibility that this 33 solar mass would be the mass of the star is less compared to what you see for the case of 45 solar mass. Okay. But obviously, yes, there are other factors. You also have to look into that. I also have to consider the other factors as well. So we cannot just exclude directly, but obviously then you need to have some other arguments to exclude it actually. Okay. It's risky to take the HR diagram all the time for determining the mass, but it is better to have something than nothing, right? So so it's always good to at least have some estimate in your mind that this is the approximate mass of the star, and then you can think about arguing and considering or excluding based on those estimates, crude estimates. Because the mass is one of the fundamental parameters, as I told you, and this is dominating, or this is basically kind of the fundamental parameter which is dictating or which will be dictating for a particular star how the star is going to be, right, in the coming years or coming millions of years, right? And if you don't know the mass of the star, the most important parameter, obviously the uncertainty will also be quite high. So yeah, that's how sometimes it's difficult to do the analysis for these stars where we do not know the mass. And it becomes more complicated when you do not know the luminosity precisely as well. Because if you don't know the luminosity precisely, you will not be in a position to find out the mass precisely. And if you don't know the mass precisely, again, the problem is actually it will be difficult. You have to consider the sequence of models, and then you have to argue or you have to see from some other sources whether you can constrain some mass of the stars and so on. Okay. Okay.